My name is Chinmay Mungale. I'm a graduate student at University of Tennessee, Knoxville, and this project is about the analysis of a hammer blow on a deformable metal. So it basically investigates the mechanics and energy dissipation during a hammer blow on a deformable metal plate. And the overall goal of this project was to understand how the impact energy is transferred during a forging-like event, both from a theoretical viewpoint as well as using a basic or a simple finite element simulation. And while the topic may seem pretty simple and straightforward at first, the physics involved is actually quite rich and somewhat complicated. So, not all the energy from the hammer strike goes into deforming the metal. Some is lost to rebound, some is lost to vibration, heat, and other such pathways. So, this project basically helped me explore how that energy is distributed and what are the factors that influence it. I began with the literature review to understand what the existing models were and what the experimental approaches to hammer forging that have already been taken or studied by other scientists. And one of the earliest works that I reviewed was by Holler, who used an energy balance approach to show how blow energy is divided. And he found that typically only about 30% of the initial kinetic energy of the hammer goes into plastic deformation. And other studies like Modwell's master's thesis looked into how the machine dynamics, like the ram stiffness as well as air pressure, influence how efficiently the energy is transferred. And more recent simulation-focused papers, like those focused by Cheng and Ameli, introduced me to concepts like the strain rate sensitivity, inertia effects, as well as stress wave propagation. And all of these concepts become very significant at high impact velocities. Kitayama used optimization tools to reduce forging energy and peak loads, and Fang showed that adjusting blow frequency can improve the material properties like strain uniformity, and residual stress. So together, these papers gave me a well-rounded understanding of the problem from analytical, experimental, as well as the simulation perspectives. Next, I'll talk about my simulation setup. So after the lit review, I wanted to at least replicate a basic or simple simulation that might showcase how a hammer might impact a deformable metal like aluminum. So I used the Abacus explicit version to model a 3D scenario, a steel hammer dropping onto an aluminum plate. I defined proper material properties, set up a dynamic explicit step, and used the surface to surface contact pairing with a small gap of about 5 millimeters to simulate a realistic impact. And one of the trickiest parts was actually making sure that the units were consistent. So initially, I had used the improper density values, and I was getting very weird results. But after changing the units to a proper millimeter ton Newton second system, I started getting results that looked a lot more realistic. So the early simulations still had a lot of issues. Sometimes the hammer moved upward due to incorrect velocity directions or the contact settings. Other times the hammer barely touched the plate before the simulation ended. So I had to adjust the step time, initial velocity, and the mesh resolution multiple times before I started getting somewhat reliable results. I also made sure to track the right outputs. I tracked the von Mises stresses, the contact pressure, and the total energy that was involved in the impact process. And the results can be seen in the next slide right here. So as the hammer approached the plate at high speed, the simulation showed that the stress waves were forming and spreading out from the impact zone. And this is what was observed in the wavefronts in the papers that I read. At lower velocities, the hammer barely caused any deformation. Even in this photo right here, you can see that the impact zone is pretty small, only uh, exceeding the diameter of the hammer, I guess, by a few millimeters. And Uh, and this photo is at a speed of 1,000 millimeters per second, and the kinetic energy at this speed was about 850 kilojoules, I guess, or joules. And I also confirmed these calculations with hand calculations, and most of this was transferred into the internal energy in the plate during the impact. So even though this model doesn't really include energy loss from heat or rebound, it can still be used as a starting point, I believe, uh, for this kind of an analysis. So the last slide would be what I learned. The first thing that I learned was actually using Abacus and FEM. I had no prior experience doing finite element modeling, and the Abacus software was pretty new to me as well. So it took me quite a bit of time to first get used to the software and then actually use some theoretical concepts that wasn't really familiar with, and I had pretty much forgotten since my bachelor days. So, as I became more and more comfortable with the explicit dynamic modeling, I think I also got better at troubleshooting the issues, mostly the contact issues that I was facing, managing the different unit systems, as well as interpreting the field versus history outputs. But it was a pretty good experience, I feel, and overall, this project as well as this course has made me appreciate the metal manufacturing industry a lot more. My experience is mainly with composites. I do have some experience with metal machining, but learning about the other manufacturing processes was definitely a pretty good experience, and I learned a lot from this course as well as from this project. So, thank you.